And so our first speaker of the day, without further ado, is Jim Wright. The title of his talk is Processing and Interpretation of Skarn-related Remanent Magnetization Railroad Property in Nevada. Jim received degrees in geophysics in 1973 and 75 from the University of Arizona and Stanford University, respectively. He has worked for several mining companies, including Phelps Dodge, St. Joe Minerals, and Newmont Mining. And currently, he consults the mining industry based out of Elko, Nevada. Jim Wright?
As Brock said, I'll be talking about processing of remanent mag. It's a current hot topic in the industry. Years past, we always kind of glossed it over. It's something we can't ignore. And what I'll do is I'll present some data for Propery in Nevada. I'll define the problem, and I'll propose a solution and implement it. Then we'll return back to the geology that I started with, and we'll see how it works in that context. So we'll get going here. The property I'll be dealing with is the railroad property. It's on the Carlin Trend. There's a number of set-hosted deposits along the east side here. I zoomed in a bit. This is not the property boundary. This is the ground mag survey that I'll be discussing. This is the boundary. But I want to give you a little bigger picture. This is the USGS reduced pole air mag. And there's a large anomaly here, and this has been termed the bullion pluton. And this is some map geology. This is the bullion stock. It's a tertiary stock. This is a reversely magnetized volcanic center graben over here. You'll see some dikes over here, and certainly magnetically suggests that the center of the pluton is to the southwest of the mapped stock. Here's the ground magnetic survey I was talking about. And it was implemented in October last year. It's 100-meter spaced east-west lines. And it's continuous reading mags. The station's about 3 meters. And you'll see we've got some gaps. This extremely rugged terrain in here, but they did an excellent job of getting the data. The important point about this is here's the bullion stock, a couple phases of it. Everything east of that line are carbonates. Everything other than the stock west of that line are clastic sediments, as well as a large area up here. A specific part of the clastic sediments is this formation. Here's the Woodward formation. It's a mudstone, sandstone. And it's said to have very minor limestone units in it. This is the results of the ground mag. The amplitude is about 1,500 nanoteslas from the bottom of the top here. This is the bullion stock you're looking at right there. This is a good example of what the sediments look like if there was no intrusion. Sediments are completely non-magnetic. So every magnetic feature you see in here is related to intrusion. It's either the intrusive rock or metasomatic effects such as skarning. So there's quite a bit in here. And this, if you kind of smooth this by eye, this is that big airborne magma. There's the little volcanic system. What I've done is I've zoomed in into the bullion stock here. This is the stock, this is the center of it. And all around it are strong magnetic responses here. And these are skarns around it. And they have a lot of them have very characteristic shape. They're bipolar, is what we call them, or dipolar, plus minus pairs. Here, there. There's a little guy right there. And this is a good indicator at our latitude that this is remanent magnetization in these units. And of course, stuff like this is almost uninterpretable. There's so many overlapping responses in here. But some of these we could deal with. Now they're small and they're undersampled. 100-meter space lines, you can see that maybe 2 or 3 lines cross that. And you wouldn't want to probably attempt to process a small one like that. One thing I want to point out is the Delmas Skarn. This was mined. A lot of historic production for the old bullion district was from replacement deposits, not skarns. But the Delmas was one of the bigger producers. And just the idea what these skarns can have away grades. Here's a quote from the paper about Emmons. on a Delmos skarn, and there's some respectable grades in this thing. 70 ounces silver, 10 copper, and 3 lead. So if you could find a large continuous one of these, they'd be worth exploring for. I've zoomed in even closer into the bullion stock and put the mag contours over it so you can get an idea of how these skarns occur. As we all know, we expect them to occur mostly in the carbonate rocks. Here's a little wedge of limestone, we get limestone. A lot of limestones over here, we get skarns along the edges. They can both be, or generally in the lime units, sort of exoskarns, but you can get some just into the intrusion endoskarns. There's a large bellmass skarn. You notice you get around this side of the intrusion in the plastic sediments, there's not much developed for a skarn. I want to talk about these dipolar anomalies. And they're produced when you have remnant magnetization, this horizontal essentially. It's frozen in a rock, it's not induced, and you run a line over it. I'll find out right away. And you run a line over it, and say the line goes right across here, and the Earth's field is mostly high angle like this. It adds here. These fields will come down the edge, you get a positive, go through a 0, and you get a negative. And that's what these dipolar anomalies are. You saw they're randomly magnetized, relatively flatly polarized bodies. And I've included the Earth's field in here that it adds to. And here's why we get dipolar responses. They come from more equate shaped bodies. They're not long, skinny things or pipe-like things. They can be modeled as a single dipole. And a lot of the history of the skarning is involved in what causes it. Multiple intrusive events break larger bodies up into smaller. There's just natural zoning skarns to get small pods of skarns. Structural history can break these things up and make them small and more dipolar. And then the carbonate rocks that are skarn can also be broken up by these intrusions. And you get retrograde effects. As skarns form and are reduced and magnetic parts removed, as alteration continues. A lot of the work on the property comes from a work by Gilliman. You'll see some of her products a little later on. Another thing about remnant magnetization is, just to remind you, is when the magnetic content, magnetic polarization in the body is frozen. It's a type of magnetization called ferromagnetism. And the finest example is C4 spray. We all remember the stripes that we used in the early days of global or continental drift and stuff. Another thing to know is the bullion stock's about 38 million years old. There's a lot of reversals in here. We could have actually had reversely magnetized stuff, and then later rotated and structurally moved it around. If one makes kind of a diagram of what remnant anomalies would look like for the Earth's field in Nevada, we're usually a declination of 66.5 inclination. Things that look like this have to be randomly magnetized. But they can also be induced something like that. But any of these highly dipolar anomalies where the inclination is flat has got to be random magnetization. So we've got to deal with that when we interpret this stuff. And we like things to be inducedly magnetized because we can pole reduce them. And so if we could somehow get our remnant magnetization anomalies around to where we can pole reduce them, it's a very attractive thing because it moves a source, the anomaly related to a source, directly over. And that's the strategy that's going to employ. We're going to try to get our randomly magnetized anomaly in a position where we can then put it in a standard processing stream and pole reduce it. So, here's our interpretive challenge. A lot of the anomalies are undersampled. And we're going to try to avoid working on any of those. In other words, there's not enough data to process. They're dipole responses, they're randomly magnetized, and they're further complicated problems in rugged terrain. It's not like we've got a nice flat surface on which we're working. So our objective is to devise a procedure to yield an approximate model. We're not going to try some high science and pin this thing down in detail. We just want an approximate model. And from that model, we want to generate a drillable target. That's our goal. Our philosophy is to accept less model detail for better estimates of general anomaly attributes. So here's our procedure. We're going to take an attractive dipolar anomaly that's well sampled, and we're going to fit it with a simple dipole model. And all we want from that is to extract the inclination declination of the magnetization of that body. We don't want to know the shape of it or anything else. All we want is to get this basic product from that. From that, we'll move on to, we'll project the mag up to the flat surface, mitigate some of the terrain effects, then we'll go to reduction flow, and we'll fit a simple model of that. And this processing flow should meet our objective. It'll give us a drillable target. So which anomaly do we want to challenge? So I actually modeled all these, and as I said, a bunch of them are undersampled. But this one really got our attention because remember, there's a line right down there, carbonates over here, clastics over here. We were astounded when we saw these huge anomalies out in the Woodward Formation, bloodstone, sandstone. And we're puzzled how something that large could be generated in there. That's over 1 kilometer long and maybe about 500 meters in width. And so we're very interested in modeling this anomaly. And this one I'm going to show you, I modeled it in 2 chunks. There's 2 big dipolar parts. And we'll look at the processing of that chunk. These are the 2 skarns. I showed you an example of Delmas. You can see the scale of the Delmas compared to that. And this was quite an interesting thing. There it is in detail. One thing I do want to point out is there's a little side anomaly right here that is not part of it, but this is practical interpretation. We can't get away from this stuff, and we can deal with this in a couple of ways. But here's an example of extraneous anomaly. This is what really piqued our attention. This is the anomaly over here, and this is residual gravity over here. And I've taken those residual gravity profiles and put them over that gravity, or over the mag. This thing is not only extremely magnetic, it's significantly dense compared to the surrounding rocks, which the Skarn would be. In fact, here's a profile. It's about a 0.5 milligallon long across that thing. It matches 1 to 1. So right off, we're thinking this is a big Skarn, and it's massive enough to produce a respective gravity level. So that was a real motivation to go after this. So, how are we going to do this? What we're going to do, we're going to fit a dipole for this thing. But remember I said this rugged terrain? Dipole's a simple anomaly, but it has to account for the rugged terrain, number 1. And here's the example. This is this anomaly. And this is the topo, and there's roughly the center. Now, we haven't returned the exact center yet, I haven't modeled it. But there's some rough terrain in here. If you computed a mag response for just a simple dipole in a steady elevation, that's what you get. But if you then compute it on top of the topo, that's what you get. And if you subtract that from that, that's the error. If you assume a flat surface, you're committing a tremendous mistake. You have to account for the terrain in your dipole model. Fortunately, the dipole model is simple enough that we can put the terrain right in and model it right off. But I just want to point out we did that. And I know the geophysicists want to see numbers, so I'll put this in here. What this is, and this is, I use this, and I don't know how many of you guys use it, but it's a thing called solver in simple Excel. It has 2 nonlinear inversion routines and a linear inversion routine. You get it with Excel when you buy it. And I think it was originally put in for financial modeling, but it's great for doing simple models. You just program up a dipole response, you put it in here, and that's all the math back behind here. You have 6 parameters for that dipole. It's XYZ location, its inclination, declination, magnitude. And then you can just say, let's invert it. And you say, you want to minimize the error function. That's the L2 norm down here, the B squared. Or you can do an L1 norm, or anything you want, minimize it. And you say which parameters, these 6 parameters, do you want to change. You can even constrain it to stay within certain bounds. So it's constrained optimization. And you can make these up for different models. Just plot your data and invert like mad. It's a great little tool. So that's what I did. I inverted the dipole response. And there's the model. I put in the raw data over here. And that's the model that it gave me. Now you know it's not a perfect fit. This is not a perfect dipole response, it will bend in here, some things like that. But what I did is I took that and subtracted and get the error in here. There's the error bar, and it's a percent error. This total anomaly peak is 1100 nanoteslas, and so I gave you a percent of the total error. And the model was a two-dimensional grid of 522 points. And I got a pretty good fit. These lows and highs are 10, 15%, except for that guy. And that is that extraneous anomaly. And the model, we could have done it two ways. I could have just cut it out with the data. But I was curious to see what the model would do, and it admirably ignored it because it's overwhelmed by the major dipole response. It just went right under it, didn't see it. And so it is very insensitive to small variation of data, and that's what we want. We want just a gross inclination and declination of the magnetization of that body. And this technique, by the way, was suggested by Ian Clark at the CSIRO in Australia. And so from this exercise, we got the gross inclination and declination of the body. And with that information, by the way, this is what it is. It's 104 degrees declination. It's actually sticking up 20 degrees. Declination is measured positive down. It's actually sticking up 20 degrees. And that's what produces that strong reading. So given that, I could then take it, I could take this data, here's the topo, the raw data, and I could level it up to an elevation of 2250 meters. I want to do this. I don't want to attempt pole reduction in extremely rough terrain. I want to level this up slightly higher than the anticipated source. And I get this, and then standard pole reduction allows you to incorporate Remanent Magnetization. You use USGS software, and you do that, you get that. That's the pole reduced anomaly. And it started out as a highly dipolar Remanent magnetized anomaly in rough terrain, and that's it right there. If you snap the profile across that anomaly, geophysicists recognize this as a pretty standard looking anomaly here. So what it's telling us is we have a shallow dipping body off to the west. That way. Next step, I was going to just use standard modeling now. We've got it out of, got the remnants taken care of, we've got it leveled up. Let's just invert it. Now we could do some exotic inversion routine here, but I don't think it warrants that. We made a lot of assumptions getting to this point. Let's just fit a simple 2.5D model. There's a block in here that will let the cross-section change, and we'll let the ends move in and out. And see how we do fit in that anomaly along the principal profile. If you do that, that's the fit. You get an excellent fit to the data. And here's the model. It generates a block like that, and I had not planned on going over here, the inversion shoving over. Anyway, that's what the body looks like underneath the topo. If you snap the profile, that's what the body looks like with the topo profile. We're extremely surprised when this happened. What we got was, we got a relatively shallow body, 30 meters to the top, dipping parallel to the terrain. But it was a slight vertical exaggeration. We did not expect that. Thinking back in our heads, we were thinking it didn't make geologic sense. There's a big, thick block of limestone in the woodruff named Skarn. And woodruff dips about 60 degrees. When this came in, we didn't know what to think. But that's what it is. If you go back to the gravity, we should have suspected this. If you look at the gravity anomaly, it acts like a flat, tabular body. It has almost equal gradients on either side. It's about 350 meters across. Flexion points there and there. Remember, the gravity's run on that slope, so that thing's about the same depth all the way down. So gravity was telling us we should have expected that model. We did indeed get that model. Geophysicists probably wondering why I haven't showed the analytic signal. This is a processing technique that is touted to ignore Remanent magnetization. If you take the analytic signal of the body, it should put a little rim around the body. So I took the analytic signal, and we got a rim. It's rough rim around here, and this is up on that plane, so as the analytic signal goes out, the body's getting down low, but it was kind of a verification that the whole process generated something that made sense. So, what does it all mean? Well, last phase, go back to geology. Here's that body. If you put it on the original air mag, it sits on a ridge of air mag, angled over to connect to the buoyant stock. But we're out in the Sea of Woodruff Formation. We shouldn't create, and this intensely Skarn, I mean, it's strongly magnetic, it's dense. It's out in the Sea of Woodruff Formation. One hint is, or at least partial story is, the work Gillerman did down here at Grey Eagle. She had several holes here that went down through carbonate, and she got to intrusion, and a long intrusive content. I expected she got a lot of Skarn. So one would think, well, okay, we got an intrusion down there, but we don't have the limestone. So what we think, the working hypothesis now is yes, we have intrusion, and we do have limestone, but where did that overlying layer of woodruff come from? And the working hypothesis is that it's a slide block off the intrusion. And there's evidence for slide blocks in this area. In fact, Nevada is notorious for slide blocks. And the intrusion came up, we got a block of woodruff came down and slid over. And it also explains why this area has been mapped and hidden in some geochem, and it never was much interest in it. But if that slide block came in after the Skarn event, it would make a great shield to prevent discovery. And that's kind of the working hypothesis we're on now. I met with the gold standard guys earlier this week, and they've already done some detailed mapping out there. They found some tremolite on fractures, and they've more magnetite than we've seen. But you just know they're not going to find smoking gun. And what's going to happen, this has got to be drilled. But I think our analysis has got us there. So there's the summary, and it kind of just rattles down. But this is the big point. The procedure gave us something we feel confident we can drill. We can take a rig in there, which is going to be expensive. It's kind of middle of nowhere. And we can get a hole in this thing, in the center of this thing. And we can also get an idea about the geometry from that dipping surface and start to formulate some ideas of why that darn thing is there. They're going to go out and do some more detailed geochem. We all realize, though, again, it's probably not going to be a big smoking gun from this thing if that woodruff got in over there after the Skarn event. So that's the summary. Before I turn it over, I just want to acknowledge Gold Standard Ventures for allowing use of the data permission to present it. Very proud. And the key geophysical services, they acquire both the gravity and the ground magnet under some pretty difficult conditions. So that concludes the presentation.
Can we thank you? So there's time for questions. Please step up to the mic in the middle of the room there and perhaps state who you are and ask questions of Jim.
I have one. I think everybody can hear me. Why did you not do infill mag, ground mag? Do you think about going to that area doing infill or maybe north-south lines? Tighten that up?
That's an excellent question. And I think in my abstract I talked about the practical aspects of exploration. We never had enough data on all this stuff. The practical aspect is we had sent the contractor in there twice to detail that anomaly. It was actually off the original survey. I don't know if you remember that outline. There was a little knockout on the west side. When we first got the data, we always saw it was a big negative. And we realized there was something lurking off the west. So the contractor went back. So we spent a lot of money at that stage. And at this stage, we may go back in detail, but I think the bottom line is the simplest thing is just to drill. We think our analysis is enough to get a hole in it. It's going to be expensive. It's pretty remote. I don't know if the track rig can get in there, but rather than turn it into a tour de force, it's just practical and appropriate. But that's a good question.
Just a quick question.
Nice days.
Are there, with respect to the depth of modeling, are there options involved with that where you could have something different, shallower than you might have as you get deeper and so on? I don't know if that's a good question or...
Well, that's an excellent question, Dave. And And that might be the case where you might want to take more data. I didn't spend a lot of time experimenting around with that version. It's just a single block. You could add other blocks to represent different phases, maybe intrusion. Yeah. But the whole objective is just get the center mass of this thing, rough geometry. You know, that's a good point too as well. That's where maybe a full-blown 3D inversion you might want to put on, you know, just because the problem is an anomaly is pretty well sampled, but real well. And I did a, you know, fitting with a dipole source, made a lot of approximations getting where we were. And again, it's just packed. Let's just get a hold on it and see what happens.
Jim, great presentation. Don't be so long.
That's on now, yep. So did you think about, or did you do and not present, forward modelling the 2.5D body, the gravity response of it, and then comparing it to your observed data? It didn't fit.
Again, I didn't, it was on a slide. That's recon gravity covers 150 meter space stations. So there's only like 3 or 4 stations across the back of that anomaly. It's not really adequate enough to model the gravity. So we just left it qualitatively saying, well, there's a gravity high correlate to this. But yeah, that would be another thing we might consider going back and doing after drilling for deposit, for sure.
Yeah, I mean, it could help, you know, constrain or give some more confidence in that
Yeah.
2.5D body. You know, really suggests that it is shallow, right?
Yeah. I don't know if you noticed up at the north end, it abruptly ended. There was a big drains there and chopped it off. And if you look at the high inflection point where that chopped off, it's down about 30 meters down the slope. That thing's a shallow thing that chopped off by drainage.
Yeah, I'm just curious, I mean, you know, you fully say that the calculations you've done have got some error bars to them. I won't say they're wobbly, but you know, they're adequate for the problem. But I'm curious, given you had some grades and some rock densities and maybe susceptibilities, throwing the next step out and actually calculating volume and an actual potential size of the target, to me would seem pretty easy. But it's sort of more of a philosophical question, I guess.
And I wouldn't want to put my name on those numbers either. We have under some sample data, and this is where guys get in trouble, is doing this stuff. And then they find out for whatever reason it's not right. I tend to think there's only one answer, it's drills and all. We can turn it into exercise. Yeah.
Jim, you mentioned that Gellerman had referenced or had some, there was some holes that had been drilled.
Right.
What was the nature of those, and were there any assays or anything to get susceptibilities or anything off of them?
I don't know. That figure came out of the report. There was 3 holes that we put in, and I don't think they must have got big numbers with her to follow them up. But she did make that section where she got this nice scar on it. But she needed limestone to do it. You don't have it out there anymore.
More questions? I'll have just a follow-up on the first question about sampling. What can you do, or if anything, to choose a line orientation to, given the a priori knowledge on remnants and then using field to sample those magnums and best mag?
I think we did pretty good with the east-west. We stumbled into that. I might rotate the lines a bit to the northwest, northwest, southeast a bit. The one best detail would be closing up to at least 50 meters. If you have a very specific time, maybe time up to 25 meters if you're really going to get into it. We did okay with east-west lines.
Okay, join me in thanking Jim.